next theorem is Cauchy Residue Theorem. So this is very important result to find the value of integration around a closed contour. Now statement is if a function fz it is analytic within and on a closed contour C except at finite number of poles z0, z1 and so on zn within C, then integration around C which is equal to 2 pi iota into sum of residue of function fz at the poles. So this is a statement. So in this way we can find the integration or around a closed contour C. Now first understand the geometry of the given theorem. So what is given? So this is a closed contour. So this is a some closed contour, anti-clockwise direction, positive direction. So the function fz is analytic at all point within C except finite number of poles. So that poles we can take it as z1, suppose z2 and so on. Here suppose z3 and z4 so on up to zn. So it is started from z0, not z0. So it is started from z1, z2 and up to zn. So these are the finite number of poles. So it means the function is analytic at each point within C, but it is not analytic at these points z1, z2, z3, z4 and so on zn. Now suppose gamma 1, gamma 2 and gamma n are the circle with center z1, z2 and zn respectively. Suppose, so this is a gamma 1 and this is a gamma 2 and this is a gamma 3, all of these are circle, and this is a gamma n. So it encloses the pole just singular point. So what we here written that suppose gamma 1, gamma 2 and so on up to gamma n. These are the circles. These are the circles with center z1, z2 and zn respectively. So these are the circle which encloses all of the singular point, and radius r so small, that they lie in the circle C, So radius are so small that they lie in the C and do not intersect do not intersect or overlap to each other. Do not intersect and overlap to each other. So it means, it implies this function f of z, so which is analytic in the annulus region bounded by the circles and C and contour C. It means, so this region, which is this part, so function is analytic in this part. So by Cauchy theorem, so that is the corollary of Cauchy theorems. So by Cauchy theorem, integration of fz into dz around C can be written as integration of fz dz around gamma 1, integration of fz dz gamma 2, so on, integration of fz dz around gamma n, these values. Now, since we know that, so this is equation number 1, integration of fz into dz around gamma I, which is equal to 2 pi iota into residue of function of z at z is equal to zi. So this is a integration of each around gamma 1, gamma 2 and gamma n. So this is for every I running from 1, 2 and so on up to n. Now substitute this value in the equation number 1. So we get integration of fz into dz around C. So this is equal to 2 pi iota, which is integration summation of r is running from 1 to n. So this is a residue of function fz at the point z is equal to zr. So this is my result. So in this way we can find the integration around the contour. So this is a Cauchy residue theorem. So this is very helpful to solve the integration around a closed contour. So remember that result. Now, to prove the application of this theorem, so I will take an example, evaluate by method of residue. So we will discuss this application by example. So what is the statement? Statement is evaluate by method of residue, so which is called Cauchy residue theorem. Integration dz over z square plus 1 into Z minus 4 around C. So where what is C? C is a modulus of Z is equal to 3. So this is my question. So I want to find out the integration of this function around a C. So solution, step number 1. What is our function? This is fz, which is equal to 1 over z square plus 1 into z minus 4. So this is my function. Now step number 2, find its singular point. Singular point या pole. So singularities of function fz are given by, singularity of a function are given by z square plus 1 into z minus 4 equal to 0. So it implies z minus iota, z plus iota and z minus 4, which is equal to 0. So it means z is equal to iota minus iota and 4. So these are simple pole, the pole of order 1. Simple pole of function fz, This is step number 2. Step number 3, check which singular point lies in our domain, our given domain. Now here the given domain is a C, so modulus of z, which is equal to 3. So if I take the contour C of this kind, O, x-axis, y-axis, so this is 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2 and 3, because it is a circle of, so this is a circle of origin 0 and radius 3. So this is a 3. So this is 3. So this is 3 and this is minus 3 and this is 3. So this is basically 3 iota positive. So this is a minus 3 iota and this is a positive 3 and this is. Now iota is this point. So it lies inside. And similarly, minus iota is this point. It also lies at this point. And what is 4? 4 is this point. So this is outside the region. So this is outside the region. So my aim is the only two singularities which lies in this circle. One is iota and second is minus iota. In my question, only two singularity z equal to iota and z equal to minus iota which lies inside the our domain. So z equal to plus minus iota and this is z equal to plus minus iota which lies inside the circle, inside the C, modulus of z equal to 1, equal to 3. So this is very important to check that which singularity lies in the our domain. Now, by Cauchy residue theorem. So what is Cauchy residue theorem? By Cauchy residue theorem, integration of the function fz into dz around C, which is equal to 2 pi iota bracket residue of a function fz at point iota plus residue of a function fz at point z is equal to minus iota, because there are two singularities which lies inside the C. So this is a question number, this is a part, equation number 1. Now, my aim is to find the residue at the point iota and minus iota. So in the first part, so as we split the function, this is a 1 over z plus iota into z minus iota into z minus 4. So this is my function. So what is first? It is a residue of function at the part z equal to iota. So what is this? This is a simple pole. So the way to find the residue, z approaches to iota bracket what is z minus iota into f of z. So what it become? So it become, because it is a simple pole, so this value will become limit z approaches iota, and here the function value is this cancel, so z plus iota into z minus 4. So this will be 1 by 2 iota, iota plus iota into iota minus 4. So this is my residue of first value. So also I can simplify. So this is a residue of a function at is equal to z equal to iota. Now second part. So I can also simplify by taking minus 4 minus iota and minus 4 minus iota. Now residue of the function fz, which is equal to z, is equal to minus iota. So this can be written as limit same z approaches to minus iota, and this is z plus iota into f of z. Now again substitute the value. So again substitute the value. So this will become limit z approaches to minus iota. So this value is equal to 1 over z minus iota into z minus 4. So this value will become 1 by minus 2 iota into minus iota minus 4. This values. So what it will become? It will become 1 by 2 iota into iota plus 4. This value. So this is a residue at this point, this is a residue at this point. Now substitute these value in equation number 1. So integration of f of z into dz c, so which is 2 pi iota. So first term is residue of, which is 1 by 1 by 2 iota. So this value is 1 by 2 iota, iota minus 4. So this value is 2 iota into iota minus 4 plus 1 by 2 iota into iota plus 4. This values. So 1 by 2 iota, this cancel with this and this. So what we get? We get pi into iota plus 4 plus iota minus 4 over iota square minus 16. So this values. So this 4 is cancelled to each other. So this is minus 17. So minus pi iota. This is iota minus 2 pi iota. So this is 2 iota over 17. So minus 2 pi iota by 17. So in this way, we can find the answer of this question. So in this way, we can apply Cauchy residue theorems to find the value of our questions, right?